4 options of C polarity and C phase, we will have 4 combinations. That means we will have SPI 0, 1, 2, 3. So which mode we have to use, that depends on our application as well as depending on your specifications. Now here if you see, we have clock polarity and clock phase. So I will just write it down: 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now in simple words, I'll say you something like, can you see this image? Okay, just
Yeah.
I think you are able to see image.
Image, not whiteboard.
Whiteboard, yeah. Okay, I'll show you. If I share whiteboard, actually I am not able to share anything else. Just to have a clear thing on this. Now, as you have 4 clock polarities and phase, you will have something like this. Okay, I'll show you in the diagram, but for now you just assume this. Okay, so here is my clock polarity. This is my clock polarity. Here my clock polarity is 0. It is starting from 0, low. Okay, so here what happens is, in clock phase, what happens is, in this mode 0, SPI mode 0, here this is SPI mode 0, 0, 0. So here the concept will be that read on rising edge and change on falling edge. Okay, read on rising edge and change on falling edge, which means what? Here your clock phase should be something like this. This is our rising edge and this is our falling edge, right?
Yeah.
Right. So here it should be something like, our data has to be like this. So here, if at all, if it is 0 or 1, it depends whether it will go high or low. Okay, so we will read this when you are, sorry, just a second. So here it will be something like this. Here either you should get either 1 or 0, and it should change at your falling or what? This is reading, and then this is your, at this particular place it should change the data value.
Okay.
Okay, so again when it is high at that time, again it should read the value. So here I have drawn some. Okay, I'll just share this with you. Just have an idea that when it is at rising edge, it have either 1 or 0. You may have any data, either 1 or 0. You will not have both, but either 1 or 0 you will have. It will read this either 1 or 0 when you have rising edge. And when the data is changing, like suppose if you have something like A, which is 65, or you any data you say 0, 48, so the value will be something like 0, 1, 1, 0, some any data, 8-bit value, any 8-bit value I have. So I am writing something like this. So at that time what will happen, here this wave will become like 0. So it will read the 0, and then it has one transition from 0 to 1. It will have a transition from 0. The next data is 1, right?
Yeah.
First it will be 0, and after that the data becomes 1. So here after reading 0, the data will change at this particular location. Here you can see this cross mark, right? It will not be both either 1 or 0, but here you will be something like the data, it will read at this particular rising edge, and then it will change from 1 to 0 at this particular falling edge.
Okay.
Okay. Similarly, if you see other combinations, then here what happens is, it will, here this will read the data at falling edge, and it will change the data at rising edge.
Okay.
If you see this, then clock polarity is 1 and this is 0. So here this will read at falling edge and change at rising edge. And this one, here you will have read at rising edge and change at falling edge. Okay, So here this depends completely. If you get this particular idea about this, I'll share that last time picture with you such that it will be clear. Okay. So
Okay.
I'll just one second. I'll just close my board and then I'll share it with you.
Okay.
Share. Straight diagram. You can see this image?
Yeah. Yes.
Yeah, okay. Now if you see here, just to check on for this particular thing, this is clock polarity 0 and phase 0.
Okay.
Okay, and just to see this cycle. Cycle is written with in front of CPHA 0, which is clock phase 0. First line is your cycle, right?
Yeah.
Right, and then here in front of SCK, just to see this C polarity 0.
Okay.
Now here if you see, when it is at the wave is at first red line, you see when it is going from low to high. Here CPHA is pointing to this 1, which means that it is reading at that particular value. Now if you see this
Okay.
again blue line, which is falling edge, the data is changing from 1 to 2. So whatever data changed, it will be in that position till again you hit a low to high.
Okay.
Or you can say a rising edge. So it will be in that position till you hit a rising edge, and then it will change the data when you are having a falling edge. In between 1 to 2, whatever you see, if that blue line, if you go up at C polarity 0, you will see that it is a falling edge.
Okay.
And then from that point to next falling edge, whatever data you see, that it will retain and it will be in that position, but it will read only when you hit a rising edge.
Okay.
Okay. Similarly, if you see clock polarity 1 and phase 0, here if you see first it is going from high to low, right? Red line. In front of clock polarity, you can see that it is going from high to low. So at high to low, it is one second. So if you see that what we said, if clock polarity is 1 and phase is 0, it will read on falling edge.
Okay.
It should read on falling edge. And see, if you see this is red line, this is falling edge. From high to low you call it as falling edge. So it is reading the cycle at falling edge, and then again it is changing the cycle at your rising edge.
Okay.
Is it clear?
Yeah.
Okay, so this all will happen when you have this SS as low. Why? Because slave select has to be. Slave select, you have SS bar, which means it will get activated when you have low. Even on that signal. So all this you can select in with respect to your requirement and all. We can say that you can select either SPI mode 0, mode 1, mode 2 and mode 3. The only difference will be where you are reading and where you are collecting your data.
Okay.
That means where it is changing the data and when you are collecting. Rising edge reading and falling edge changing. This will depend on your SPI mode.
Okay.
Okay. So now if you see this next, if you have understood this, so we will have two things again. One is reading and the other is writing, right? We may have to read as well as write the data.
Okay.
So how to read or write that particular data in, I'll not say you that particular registers pertaining to one particular, this is in general. Okay, this concept is general concept and not pertaining to any particular controller. Why? Because in 8051 we don't have SPI controller, and if I want to explain you completely thoroughly in AVR or ARM controller, first you should know the basics of that, as well as you should know the registers of that particular, like we had timer register and serial communication registers, we should know even the registers of some other controller also. Then only we will be able to write the program. So what I am
Okay.
trying to do is, we will implement this later, but as of now I am explaining you the general concept of it.
Okay.
Okay, now if you want to write, as I said you, we will have two things. One is write and the other is read concept. Okay, so if you want to write first, the steps involved will be, okay, I'll just have the board. Now, if you want to write first, then the steps, some steps will be there. How to do that? First of all, we know that whatever we have, this CE, or you can say this clock select, has to be 0, right?
Okay.
See what just now we have said, that chip select, or you can say that what it is, SS, slave select. We will have multiple slaves. Okay, slave is nothing but whatever device is connected to your microcontroller through and your microcontroller is operating clock for it, or providing clock for that particular device, you call it as slave, and whoever is providing clock, you call it as master. So you can have one master and multiple slaves. That means a single clock from your microcontroller can be provided to multiple slaves. It can be SD card, or it can be memory card. Sorry, memory and SD card are same. SD card, or you can say it can be any other device like EEPROM, anything. Whichever is having SPI communication, whichever is operating on. So how to write the data into it? That means, now if you want to write data, that means what? From microcontroller to slave, you are saying, or from slave to microcontroller, anything. But here you will have to follow some steps. What is that step is, first of all, we will have this we will have some pins for it. Okay, or we can say clock, you say, or sometimes we will have some particular pins around it. Like if you remember, just now we have done something like in what we have done, we have just given that particular pin as low, then only it will start working. Some concept we did where we have to make that particular bit as low, and then only it will start working.
Yes,
I think what concept we did where we have to make that particular bit as low to interrupt sizing. Yeah. Interrupt. Okay, so like that, here also we will have something like chip enable CE, or you can say SS, anything. So for that, first of all, we have to make that particular signal as low, then only it will start working. Okay, and then after doing this, then we will, that means we have selected which slave we want to work with. Okay, after doing that, our microcontroller has to provide clock. Okay, so we will be providing clock to your master as well as slave. So this will be something my clock. And after that, what we will do is, first of all, when you are writing something into our device, then you should have address of it. Okay, so here we need to send, after that, through this pin, which is like master out or slave in. So here we are using something like master out and slave in, because here we are doing input to our slave. So master out, slave in, that means whatever output is from our microcontroller or master, it is an input to your slave.
Okay.
Master output is slave input.
Yeah.
Okay, so here what it will do, again, it first we will have to send a address of it. So first we will be sending address, and this should be an 8-bit address. Okay, and here you will have you will be shifting only one bit at a time. So
Okay.
here what you will do is, first you will be sending address, but here you will have something like, you will have bits like A7 to A0. This is our address, okay?
Okay.
Whatever data we are changing, it will read and write that with respect to SPI mode 0. I am not showing you all these things, okay? With respect to clock, it will change and it will read and it will change depending on what mode you are selecting. As we are simply drawing it, I am showing this. So if you want to write data, here this bit has to be made 1. Okay, so this bit will go first. So when it detects that this A7th bit is 1, at that time what happens, it will understand that it is going to do write operation.
Okay.
That means you are going to send your data and store it into your your slave.
Okay.
Okay, and then after sending 8 bits of data, what it will do is, first then again you will be sending your data. Then after this particular bit, you will be sending your data, which is of, depending on how many bits you want. I am saying 8 bits, so you will be sending D7 to D0.
Okay.
Okay, so after sending this A7 to A0 and D7 to D0, just to make this at that time, here it will read all the data, which is nothing but your the second other device will read this A7 to A, and at that particular address location, it will store this D0 to D7 data.
Okay.
Okay, now this is for single byte. I am writing only for single byte, right? D0 to D7. Only one byte we are writing. But generally when we are displaying something, if you see your LCD screens or LED screens on railway stations or some advertisement purpose, you are not using only one byte. You will be seeing multiple characters at that time, right? So that is called burst write. Burst write is a chunk or a group of characters, you can say. So at that time what we will do is, so first we will be here, this is for single byte, okay, only for one byte. So we will write here for multiple bytes. Multiple bytes, suppose say 10 bytes. I'm just giving an example of 10 bytes.
Okay.
So here what we will do is, same concept we will use, okay, but only at starting we will provide an address, that's it. We are not going to provide address again and again. Again this bit will be 1 to indicate that here this is a write operation. After providing this first address, then continuously we will be sending data. So here I am just calling this as data as DA. So here you will be sending data something like 0, 1, 2, 3, 4 continuously. How many bytes you want to send is 10. So I will be writing something like 0 to 9 bytes of data. Okay, now the question arises that first address we are providing, and that at that particular first address data or first byte is stored, right?
Yeah.
First byte, this particular first byte is stored at this particular location.
Okay.
Address location. What about second to ninth, or you can say that this is your first to ninth byte. More 9 bytes are there which has to. So once you store this data, automatically the address location will be incrementing. You need not say continuously that, okay, store my data 1 at this particular location, store my data 2 at this particular location.
Okay.
Okay, so simply for the first time you will be providing your address, and then after that for multiple bytes of data you will be providing only data, and you are not going to change your address. So sequentially your data will be stored at that particular location. You will be providing address only if you want it. I don't want to have it sequentially. I want to store my first data at some 53H location, and after that if I want to store the second data at 65H location, at that time with single byte, because there you will be providing single address for single byte. If you want to store the data in sequential manner, so or multi-byte is okay, then at that time we'll be providing only first address location and then it will do multiple bytes. Okay.
Okay.
Similarly, if you have reading option, at that time only the same thing follows, but the thing will be here you need to make this A7 bit as 0. When you make this A7 bit as 0, at that time it will understand that you are doing reading operation and not writing operation. That means, for example, if I have some data in my memory card, I have one file or data at particular location in my memory card, SD card, which is connected to my microcontroller, and I want to fetch that data. At that time, first I'll provide the address of the particular location where my data is stored along with the 8th bit as 0. When it reads this 8th bit as 0 or A7 bit as 0, it will understand that it is a reading operation, and then here this from this particular location to A0, it will find out what is the address. And from that particular address location, it will fetch this particular data of D0 to D7.
Okay. Yeah.
So here, two things you have. First, a 0 bit, and then whatever location is there here at this, as this is an in, then here your microcontroller becomes input, right? Here we are sending data, so your master is output. If you have master input, at that time on this second line which we have, which is MISO, master in, slave out, at that time you will be sending only address from master to slave, and this data will be provided on, data will be provided at this particular line. You will be writing it from master to slave, but here you will get your output at this particular line, which is master slave out, which means from slave you are sending it to master, which is slave output and master input. So in reading option, you will have to first send the address along with first bit as 0, which is an indication of read, and then whatever output you get, you will be getting it on the second line, which is MISO, and you can read that. Again, this is a single byte operation. So similarly, if you want to do multi-byte operation, same thing you have to do. First give the address location and ask the data. Okay. So now you may have some questions regarding this, which we will see now. We will see an example for it. So here what we will do is, we are not going to write one program, because here the program is completely with respect to registers. Okay, so what I'll just show you an example with your what you have, some byte of data. Okay, so now here if you see this, this is for read operation, as we said. And okay, you may have a question that if I'm saying like this, at that time how your microcontroller will understand that where it should stop. You understood my question? Here I am saying that I am giving here for 1 byte also or for multi-byte also. What we are doing, we are simply providing in one address. Whether you want to write or read, doesn't matter. But when you are providing A7 to A0, A7 to A0, it means either you are writing or reading. But how it will understand that it is a single byte or multi-byte? Because at last we are not providing anything, right? So that will be with respect to this CE. Once you make this particular pin high, it will communication, which will an indication of end of this operation. Either it can be write or read. Okay, so here we are using 4 lines: MOSI, MISO, SEK, and the CE pin. Or you can say S pin. So once you stop that, it is an indication of that yes, it might be 1 byte data or your multi-byte data. Okay, so here
Yep.
you will have, depending on the controller which we are using. This is clear, right? This is the basic
Yeah,
concept you have.
yeah. Okay.
Because you go for any register will change.
Okay.
So here what you will have in, now the second thing you will have is at what speed we are doing communication. Because even when you are using UART, you will have some speed of communication like 1200, 2400, 4800 or 9008,
Oh,
sorry,
600.
yeah,
Oh,
9008, 200, or you can say 115200, some speed you have, right? Here also you will have that
yeah.
particular speed. Now that depends
Okay.
on your register. Okay, that you will have to select with respect to select register, like you are working with ARM controller or you are working with what AVR controller or PIC controller. With respect to some particular SPI registers, you will have some bits provided. Like we have
Oh,
T0, TH0, TH1, or if you say SCON, you have some bits like TXD, RXD. Some pins will, some bits will be there, right? So like that,
yes.
we have some particular registers related to SPI also. There they will provide that some particular bits will be provided through which you can select frequency or you can say baud rate.
Okay.
Okay, so if we want to see an example, we will go with AVR. Okay, so if we go with
Okay.
AVR, I'll just download your data sheet for AVR once, which
Okay.
just a, okay,
Yeah.
data sheet. Okay, HTML Mega 16 data sheet. Now, I think you can see this data sheet.
Yes, yes.
Now, if see, this is our SPI communication. Okay, so
Okay.
here if you see, this is visible, right?
Yeah, yeah.
Okay. So here, as we can see this, there will be an 8-bit register, one bit we will be receiving, and your master will be providing a clock generator.
Okay.
You can say that CE pin or you can say SS pin are same. So we are using
Okay.
4 lines. One is master out slave in, master in slave out, SCK, and SCK is for system clock, and then other one is your or SPI clock, and the other one is SS, which is slave select, which slave you are working with. Okay.
Okay.
So if you see here, okay, if as we discussed, MOSI is your user defined, which means like either master is sending out or receiving. Okay, MISO is an input. Master can ask the slave to provide output, but your slave cannot say master, slave cannot ask data. Now if you are connecting your laptop with your SD card, you can say your SD card whether you want to write or read from it. Your SD card can't say your microcontroller or your laptop that I want to write or read into your laptop.
Yeah.
Correct. So here your master SD card will be your slave, and your laptop will be your master. So master MOSI is your user defined, but MISO master in slave out is your input only. SCK is user defined, and this we can select. Now if basically we want to see registers or how we can select the frequency and how what type of registers we will have here.
Okay.
So in datasheet, they will even provide your assembly code as well as C code for your basic understanding how it is working.
Okay.
See, one control register is there called SPCR, which is SPI control register.
Okay.
Okay. So even like we have an interrupt for timer interrupt, then we have serial interrupt, like that we have SPI interrupt also. That bit we can enable by using this 7th pin. If we make this particular 7th bit as 1, then SPI interrupt will be enabled or it will be working. Okay. Then you have one particular, to enable your SPI communication, you need to make this particular 6th bit as 1. When you make this SPI communication is provided, which has multiple options. One is either it is working like input output, and the alternate function is your SPI, right?
Okay.
We are not dedicating particular pins of our microcontroller to SPI communication. We are using the pins which are having some alternate functions. Okay, so to say that the pin should not work like input output and it should work like an SPI, we need to make this particular bit as 1.
Okay.
Which will say that yes, now your SPI is enabled, and those pins which were working like input output will no more work like input output.
Yeah.
Okay, then we will have something like data order. Where that register went off. See, here we will have data order, which will say that here data order will say that whether you want LSB to go first or MSB to go first.
Okay.
Okay. So here we can see that when the DORD bit is 1, then LSB is transmitted first. That means your data will be transmitted first from D0 to D7 bit. And when your data bit is data order is 0, that particular bit is 0, at that time the data will be transmitted from D7 to D0.
Okay.
When it is 1, first D0, you have one shift register, right? At starting we have seen that SPI will have some shift register. In that shift register, whether when sending your data, whether you want to transmit, I will show you that. Wait. Can you see this image?
Yeah.
Image, SPI slave interconnection.
No, again it went up. I'm seeing only the data sheet.
Now you will see.
Yeah.
Is it visible now?
Yes, yes, yes.
Hello? Yeah.
Hello.
So now here you can see this is a shift register where you have LSB as well as MSB. So here if you see, if you have something like, if you are considering something like MOSI, second line operation. So first here, from here MSB is going first.
Okay.
Second dotted line if you see.
Yes.
If you see this dotted line, so first MSB is coming out and then again it will shift one bit by one bit and that bit will come to MSB again.
Okay.
So here this with this particular bit you can say that whether you want to send out LSB first or MSB first.
Okay.
Okay, then you have master, C polarity, C phase, SPR1, SPR0. Now these bits are for, if you see this, master or slave select. Okay, then if you have make this particular bit as 0, it will start selecting when you want to connect it to some other pin, then you will have to make this pin as 1 because this is
Okay.
master or select. When you write this as 1, then your SS will start working, which is slave select. When you keep this SS as low to particular pin, at that time that particular device will get activated. Next you have clock polarity. Already we discussed this. You can have two things in clock polarity. Either you will have rising edge or falling edge. Okay, and depending on these two as well as the other two, 4 bits we have. So that 4 bits we will have to select. See, this is your clock polarity can be either 0 or 1 and clock phase can be either 0 or 1. Right? So then here it says that depending on these 2 bits you can select either the SPI communication mode, whether it is 0, 1, 2 or 3. Because we are dedicating 2 bits for it, you will have 4 combinations. Next, the last one is your last 3 bits are for selecting your oscillator frequency. With what frequency or with what speed you want to communicate with your master or slave. Okay. So here if you see, just to leave this SPI2X, if you consider only this SPR0 and SPR1, consider only these two. You will have 4 combinations 0001, 1011.
Yeah.
Only consider SPR0 and SPR1. Leave SPI2X. Only this particular 4 options if you see. These 4. Leave the third line SPI2X. Only SPR1, SPR0. You have 4 combinations 0001, 1011. Right?
Yeah. Yeah.
Again last also you will have this only. But when you make this particular bit as 0 or 1, so here if you say, if your F oscillator frequency, it is divided by whatever F oscillator frequency is, that will be divided by 4. If you have SPR1 or SPR0 as 0. When you have these bits as 0 and 0, whatever your F oscillator frequency is. For example, your F oscillator frequency in 8051 is 11.059 megahertz.
Yeah.
Right. So depending on your controller, what oscillator frequency you are connecting will be divided by 4. Suppose you have 12 megahertz crystal oscillator or 16 megahertz crystal oscillator. So 16 by 4 is
4.
6. You will get 4 megahertz speed. Okay. Similarly, if you have 16 by 16, you will get 1 megahertz speed. Similarly, divided by 64 or 128. Okay. These speeds are there. Now, here you have SPI2X bit. When you have this bit as 0, this will work simply, F oscillator by 4. But when you use or make this 4 bits as 1, SPI2X bit 1, it will multiply it with 2.
Okay.
Okay, SPI2. So SPI2X is nothing but multiply it 2 times. So f oscillator by 4 into 2. You will get f oscillator by 2 frequency.
Yeah.
Here you had f oscillator by 4, right?
Okay. Yeah.
Multiply it with 2 times. F
Okay.
oscillator by 4 into 2. So 2 2's 4. You will get f oscillator by 2. Similarly, you will get f oscillator by 8, 32 and 64. 4 by 2 is 2. 16 by 2 is 8, 64 by 2, 32, 128 by 2 is 64.
Okay.
Simply, when you make this bit as 1, you are multiplying whatever frequency you had with 2. When you make it as 2, you will get this particular option. So this is how we are selecting your clock frequency in AVR microcontroller. Similarly, you will have multiple options provided for different controllers. Say here also you will have some registers for status register. SPIF is whether your operation is finished. At that time, this bit will become 1 to say that yes, our operation is finished. Sometimes there can be a collision during data transfer. Okay, so here first, without reading the data, whenever you are writing this, and sometimes you are doing reading or writing operations, at that time what will happen? I don't know what I'm doing, whether I'm writing or reading, or some operation might be already under process. So at that time, what we will do is first we will monitor this SPIF flag, and if that flag is high, then only we will clear and do next operation. And while writing this, while doing the next operation, we will make it high such that you can access the data register and no one else should access that data register, because already my operation is work, I am doing my operation. So at that time, that particular register has to be with me and no one should access it.
Okay.
This is simply we are taking this data register under our control. Like we have SBUF register, we have here SPI data register. SBUF register is there in 8051 serial communication. Like that, we have here the data will be collected in this SPI data register. Okay, and this all are your reserved bit and SPI 2x bit. So like this, we have this particular register through which you can select it. This is your SBI register. You'll have LSB and MSB, and this is your where your data, you will receive the data as well as to transmit the data. This is the register.
Okay.
So already we have seen this data modes, right?
Yeah.
Mode 0, mode 1, mode 2, mode 3. SPI. Okay. Now if you see I2C, I2C is again a 2-wire interface. Just a second.
Okay.
Just a second, Kaushik.
Yeah.
Nahi, Papa. 1 minute, beta. Hello. Hello.
Yeah.
So sorry.
Okay.
Okay. So here we have again 2-wire interface, which is I2C communication. Like we have SPI communication, we have one more communication which is I2C.
Okay.
Okay, so here you will be transmitting it the same way. You will have some address, you will have some data like that, but here you will use only 2 lines. There we were using 4 lines, right? Mostly MISO, SCK and CE or SS. Here you will only use 2 lines, that is your clock and data. That's it.
Okay.
No other lines will be used, only two lines will use, and that's why this is also called two-wire interface.
Okay.
2 buses, or you can say 2 lines or 2 buses, anything you can say. And here both master as well as slave, that means the data from master to slave and slave to master is supported.
Okay.
Either your device can be a transmitter or receiver, anything is okay. There what we said, only your master have the full control in SPI. Here there what we were doing is, your slave cannot send instruction to master without asking some data or storing, writing or reading data. Independently your slave was not operable, but here you can transmit or receive anything from it. Then here you can connect around 128 different slaves to your line. That means on 2 lines you can connect 128 devices.
Okay.
Okay, so only one microcontroller and 128 different chips you can connect, and you can communicate using only 2 lines.
Okay.
And here if you have 2 masters, then you will have some option called arbitration, which we will see next. And after that, here you have data speed. You can see data speed is different with different microcontrollers, that we will have to check out the data sheet for that particular microcontroller. Okay. Next, if you see here, this is your device, these are your devices, and this is your line, SGA and SCL. Device 1 and device N. How many lines you want to connect, you can connect.
Okay.
Okay. And here you have this terminology, same thing. Master generates clock, slave is used by master to address which slave we are using. Transmitter is the one who is placing the data on the bus, and receiver is the one who is reading the data from the bus.
Okay.
Now if you see this, now this is your transferring the bit. How to transfer the bit, or what is the format or frame size? Like we had frame size for 8051 start bit, stop bit, and whatever we send in between start and stop bit is our data. Like that, here also the data is formatted between a start and stop bit. Okay. So here this is your clock and this is your data. SCL is your clock and SDA is your data.
Okay.
Okay. Now whenever here you have, whenever this is high, when your clock is high, at that time the data is stable. If you see this SCL line, this is from this bit to this bit, the dotted lines. Before dotted lines, whatever is there, it will be read only when this data is high. This SCL line is high.
Okay.
Okay, and the data will change only when this is low.
Okay.
Okay, so here we have a start and stop condition. I think the next image may have that start and stop condition. Okay, now if you can see this, right? You are able to see the data sheet, right?
Yeah.
Okay, so here if you see, when your clock is high, can you see this SCL line?
Yes. Yeah.
I am unable to select it actually, otherwise I can make it something like blue such that I can select it. So when your SCL line is high, at that time what we are doing is, we are giving a high to low signal on our data line.
Okay.
When your clock is high, and if you are giving a high to low condition, that means 1 to 0 on your data line, it consider it as a start signal.
Okay.
So when clock is high, if you consider it as 1 to 0, then it starts. And similarly, when your clock is high and if you give a low to high signal, it consider it as stop. In between whatever you give is your data.
Okay.
Okay. Now if you see this, see, when in between data, suppose I am sending some data, and in between what you do is, when your clock is high and you want to change your data, or you can to change your data from 1 to 0 or 0 to 1, and you do it when your clock is high, at that time it will consider it as stop bit.
Okay.
So you have to be careful that when your clock is high, if you give a high to low, it will consider it as start, otherwise it will consider it as data.
Okay.
So now this is clear that if clock is high, a high to low signal is start. When clock is high, low to high signal is stop. Okay. Now how to read that data, or how to send this data? Now if you see this, once you give a start signal, here we have given a start signal. Now first you will, like we did in SPI, here also first you will have to give address.
Okay.
Okay, first we will have to send the address, and here also we have to say that whether we have to read or write, and then we have to use acknowledgement. Here acknowledgement is simply saying that yes, I did receive it. You're sending a particular bit. Now if you see this, see this. So here your data is MSB. And now if you see this, your data is here. Your data, when your data, when your clock is high, after your clock, when you give a start signal. Okay, once you give a start signal, when start is nothing but high to low, at that time from next cycle onwards, whenever your clock is high, it will read the data, and when your clock is low, it will change the data.
Okay.
Okay, if you see here the cross line, here in between 1 to 2, when the clock is low, the data is changing.
Okay.
When your clock is high, it will read the data whether it is 1 or 0.
Okay.
And after that it will give repeated start and stop condition will be there. I'll show you that. Can you see this figure 81?
Yeah.
Now if you see here, first we are giving a start signal, and then we are giving your address, and then we are saying whether we want to read or write, and then we are sending an acknowledgement signal. That acknowledgement signal, suppose you are giving it as 1 or 0. Okay, at that time whatever you give, now next byte will be, this is only 1 byte of data. Okay, address, read or write, and then your acknowledgement bit. The next thing will be whatever you send next is your data. Then you will be sending, first is, if you see here, this is address plus read write, and then here you have the data byte. You will be sending 8 bits of data along with one acknowledgement bit.
Okay.
And then you will be giving a stop signal.
Okay.
Same thing you will have it like you will have single byte as well as multi-byte operation.
Okay.
I'll show you that. I have one pic with me. I'll say you, but first I'll just say you whatever data is there in this data sheet. Now if you see this 83 figure 83, we have something called arbitration. Okay, now what is this arbitration thing? Now suppose I have 2 masters. Okay, and I have started. Now whom I'll be selecting? Now I have 2 masters. I am saying that I want to use this line, and the other one is saying, A is saying I want to use, and B is saying I want to use. We have only 2 lines, clock and data. So whom the preference will be given? Whom the preference will be given, that who can use that lines in between A and B.
Okay.
You understood what I'm saying? Here you will have something like, first you will be, they will be asked, here I have some option like I want to use, we will have, as we said, anyone can transmit and receive data, right?
Yeah.
When we
Yeah.
can use this, anyone can transmit data, I can have that two or three two people, something like A device and B device, want to come. Will do is, after sending something like here, the preference will be given to address. Can you see notepad?
Yeah.
Can you see notepad? Now here, suppose my here what I can say is here, just a second.
Okay.
Now I have two devices called A and B.
Okay.
Now A wants to connect to a slave whose address is, suppose 0010 000. As we said, we have 7-bit address. As we have 7-bit address, the 7 combinations we get is 128. 7 bits combination, 2 power 7 is 128. That's why we will have maximum of devices we can connect to is 128. Okay. So
Okay.
I want to connect a device whose address is this, and B wants zero 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 one. Suppose we have something like this. Will happen. So first it will send this particular thing. It will send this address 00. Both have zeros at first bit. I mean high.
Yeah.
MSB both are zeros. Second also MSBs both are 0.
0.
Fifth, 7th bit is 0. 6th bit for both the A and B are zeros only.
Okay.
Right. At third bit, which is nothing but 6th bit, your A have 1 and B is 0.
Yeah.
Third bit, here you have 1.
Yes.
This is 1 and here this bit is 0. So the preference will be given for B, and B will be able to continue the operation, and after the completion of its operation, the data lines and clock lines will be provided to A.
Okay.
This particular thing you call it as arbitration.
Okay.
So first it will check whether the address. So simply it will, who encounters 1 first, they will lose the ring.
Okay. Okay.
Okay, so this is called arbitration, and if I say you one simple example of how this data is working, I'll show you something. 1 second, I'll just draw this particular thing.
Okay.
You can see the whiteboard, right?
Yeah.
Now how we are sending data, we will see one example, and after that we will see the registers which are involved in I2C also for AVR microcontroller. Okay, now my master is going to address a slave whose address is something. My master is sending some data to slave. Okay, the slave's address is something, we will take some 00, some random address. I am saying 110110 011. Sorry, 7-bit address, right? So my master is going to send suppose is something like 10101010, which is AA.
Yeah.
I'm saying some random data. Actually 1010 we will not going to send AA, but simply we are sending some particular data 1010. Oh no, we will do one thing. Here I will send it as 0, such that we will see able to see that next also if we have in continuation zeros, what will happen. Okay, now this is my
No.
address, this is my address, and this is my data, which I want to store it at this particular address location, right?
Okay.
Now first what will happen, first I have to give my clock, right? So when my clock is high, at that time if I'll give a high to low, this is considered as my start.
Yeah.
So this particular thing is considered as my start thing.
Okay.
Now next, let the clock be something, I'm not bothered about it, but with each clock cycle some data will be transferred.
Okay.
Is high, right?
Yeah.
But my data is 0, right? So I will have to write it some, okay, this was not my clock, right? One second, my clock is this one. So this is my clock. So this is my clock. Now after giving a high to low condition, now when my clock is high, at that time I need to send the address. So my address is 0 first, right? So I'll be sending 0. After that what I need to do? Next is again 0 only. So I'll continue here with, till here I'll continue with 0. This is my first cycle. My data is read at this particular location. This is 0. Okay, and next this is my 0. So this becomes again 0. And now at next clock high, I'll be reading it like 1.
Okay.
So here I'll read it like, when the clock is high, my data is also high. And then again at this particular location, I'll be having high.
Okay.
Okay. Or else here you need not give it, as you have, or you can simply say here 1. So I'll just, till this time I'll keep this condition as 1 only, because next bit is also 1. So here again it will read like 1.
Yeah.
0 0 1 1, right?
Okay.
And then again we have 1 0, which will be read at this particular location. When the clock is high, this bit is 0, and then next you will have something like 2 bits high. This is 1, and the next is also 1 when my clock is high. So here the 1 is read, and here also 1 is read.
Okay.
This is clear?
Yeah.
Right. Now next what we are sending is your read or write bit, whether we want to read the data or write the data. So we know that we are writing data. So for writing we need to send bit 0. When your clock is high, again the same thing, give a bit as 0. So here it will consider it as, after sending this particular address of 7 bytes, you need to send 108th bit to write it, whether you want to write or read. Okay. And then we are sending some acknowledgement also as 0 only. So when we say this acknowledgement bit also 0, so here this is 0, we consider it as acknowledgement bit. Okay. So here in this way we are sending first start condition, and then whatever 7 bits is there, those are address, and we are sending, I want to write into it, and so we are sending an acknowledgement signal. Okay. Next, what will happen? Whatever next thing you are sending, the same way you will have to send your data. So my data will be, I'm not writing my clock again, or I'll simply draw the clock again, nothing will happen. Fine. Okay, so here again same thing. My data is something like when my clock is high, I'm giving 1 signal, and again when my clock is low, I'm giving a 0 signal. Next again 1 and then 0, 1. Oh, next we gave zeros, right? First we gave 1 1 1 0 1 0, and next is 0 only. For 3 bits we have next as zeros only, and then again 1 1 and then 0.
Okay.
You read at this location. When the clock is high, data is 1. When clock is high, again data is 0. Clock is high, data is 1. Clock is high, data is 0 0 0 0 0. 3 bits are zeros, and then we have 1 here. Sorry, this is 1, and again this is 0 when the clock is high. Okay, and when you get an acknowledgement bit as 0, you will have to respond back with acknowledgement bit as 1. So here if you are giving acknowledgement bit as 0, here you need to give not of acknowledgement, which means here you need to send a byte as 1, because here acknowledgement bit was 0. So here the not of acknowledgement bit has to be 1, and then give a stop signal. So when my clock is high, we are giving a low to high signal, which consider it as stop.
Yeah.
So from here to here is my clock stop signal. So in this way we are sending your I2C data. Okay.
Okay.
Now here one more thing we have. Okay, and that is suppose here what happens, you are calling some slave. Okay, and you are asking it to provide some data, but your slave is not ready for that process. Okay, what we are trying to do is we are asking some data to your slave, but your slave is not ready to respond back, or it got hanged, or it is taking some time to process that data or something. So at that time there is one thing called, what it will do is it will not release the clock cycle, it will hold the clock. So the clock cycles will not change from high to low.
Yeah.
Okay, so when the clock line here, what it will do is it will simply, your clock is becoming 1 to 0 0 to 1, right? So when your clock is not when your slave is not ready, it will simply hold this line.
Okay.
So when it is holding this line, at that time all the operations will be stopped. So when your when the master is unable to generate a clock, it is called clock stretching. You are stretching your clock to stop the operation or to hold the operation for some time.
Okay.
Okay. So here also we will have same thing, like first we have seen only one byte of data, like we have in SPI. Here also we will have something like multi-byte or multi-byte burst write or burst read. So for that also same thing here. First we need to give a start signal and then give address. After giving address, then what we need to do is give a write or read signals, right? Then give write or read signal and then acknowledgement, right?
Yeah.
This is address and this is acknowledgement. So after this, whatever you are sending is your data, right?
Yeah.
So here we are writing something like first. Now here you have one more thing. When first of all, when I have multiple slaves, okay, suppose I have 2 SD cards. So first I need to give the address of that SD card. So first address indicates the device address.
Okay.
That device address is provided by your manufacturer.
Okay.
Okay, so here this device is to select which slave you want to work with. I want to work with first slave. We have 128 slaves, right? 128 devices are connected.
Yes.
So which device you want to work with? After
Okay.
selecting one particular address, which is suppose slave 1, after that again you will have to send one address. This is the location of the memory where you want to store the data or when you want to write the data. This is to
Okay.
select the device, and this is to say in this particular S1 device where you want to store the data.
Okay.
If you have SD cards or two SD cards connected to your laptop. Okay. So before
Okay.
transferring data, will you select which device you want to transfer data with? Yes. You will not simply
Yeah.
transfer the data. You will select, or you will see at least that which is the particular USB device I want to work with. So similarly
Okay.
here, now after you say that I want to work with some SD card 1, USB device 1, at that time you will open and you will see that if I have some particular folder of books, so you will give that book's address here, that I want to store my next book in this particular folder or this address location. Okay, so this address is to provide in this device where is this address location, and then again what we will do is we will give an acknowledgement. Here you need not say whether you want to write or read. Why? Because already we have mentioned that in this device we are going to write or read, do read or write operation. So we need not say it again and again. After selecting read or write, simply go give the address location and then send acknowledgement bit. After sending acknowledgement bit, now whatever you are sending is your data. So data 0. Next again acknowledgement bit.
Okay.
Next again data 1. Acknowledgement bit, and so on till you give a stop signal.
Okay.
Okay, so here this again same thing. The data, once you give a particular address of D0, then the next data will be stored at next address location. If you give this address as suppose 000, then the data will be something, suppose here the data is something called 73, and the next data of 75 or any value will be automatically incremented to 0, 1,
Okay.
2, 3, 4. How many data you give, that many address location it will provide or increment.
Okay.
Okay, this is for write operation. When you want to do read operation, so here read operation is also same, but only thing what we will change is we will have to say select the slave, we will have to give a start signal, we will have to select the SD card from which we want to read, and then here for we need to first give read or write thing. Okay, now
Okay.
you are writing this address. See here also, after first time you need to say that I want to write into it. Whether you are doing reading operation or writing operation, you will have to give 0 only, because the next byte, this address location you are writing, you are selecting this address location. So you need to say that I want to write the next data whatever is coming into my device. Okay.
Okay. Yeah.
But after selecting this device, here you need to give in between this acknowledgement and this, here you need to give a read signal that from this address location I want to read the data whatever comes next.
Okay.
To write this address we are giving write bit as 0. But from at this address location I don't want to write, I want to read. So after giving the second address, give read operation signal, not directly
Okay.
acknowledgement. So after giving a read signal, next whatever you have, that is your data to read.
Okay.
Okay, so this is about the operation which you are performing in your two wire interface, or you can say your
I2C.
I2C. Okay,
Okay.
now here if you see, we will see some particular register. You understood the concept of it?
Yeah.
Okay, so here if you see, here also we will have some speed, we will have some registers related to it, we will see that registers. We will write a program, but when we work with some other controller, then we will write the program.
No.
Because directly understanding and using these registers becomes somewhat confusing. And
Okay.
we don't want to get confused. The only concept is right now enough. See, here you have how to select the frequency. The formula for selecting the frequency is CPU clock frequency by 16 plus 2 into TWPR into 4 power TWPS. Okay, so here the TWPR is the bitrate register. This is one register where we are going to load a particular value. And TWPS is your prescaler. Prescaler is nothing but if you have something like 1 or 2. You can see this notepad, right?
No, only seeing the drawing board.
Only drawing board. Okay, you are not able to see from that time data sheet. Okay, I'm so sorry. I was browsing data sheet and I was saying you the formula also.
No.
I don't know why it is not allowing to use whiteboard as well as these registers can. So you can see this formula now.
Yeah.
SCL frequency is CPU clock frequency by 16 plus 2 into TWBR into 4 power TWPS.
Okay.
This is the formula. So at what speed we want to work with, we know that. If I want to work with 9600 or 115200, I know that. So by simply substituting this value, we will find out what is this TWBR register and we will load this particular value in that particular register.
Okay.
Okay, this is nothing but bit rate register, TWI bit rate register. Okay, and this TWPS is nothing but prescaler bit, which we will see now. Now here if you see, this is your TWBR register, which is here. Suppose if you want to have some particular frequency of, I don't know one example is given or not, but 9600 suppose. So I will have to find out if I want 9600 frequency. By using that formula, I will have to find out TWBR value. That TWBR value I will have to load in this particular register. Like if you remember, when we were using your serial communication to get that particular speed, we were dividing it by 3, 6, 12 and 24, right?
Yeah. Yes.
Similarly, here also, to get that particular value, we need to load that 3, 6, 12 or 24. With respect to here, whatever value are, we need to load that value in this particular register.
No.
Okay. Similarly, we have one control register for TWI. So first is again your interrupt flag. If your operation is finished, then this bit will become 1 to say that your operation is completed. Next we have acknowledgement bit, which will enable whether you want to have an acknowledgement pulse or not.
Okay.
Okay. Next you have TWSTA, TWST0. and this bit is for, as we have 2 bits, we'll have 4 conditions. Whether you want to have 2 stop bit or 1 stop bit. TWA STA is to start the condition bit. If you make this particular bit as 1, it will give a start condition, and if you will make this stop condition bit as 1, TWST0, then it will generate a stop bit signal.
Okay.
Next you have write collision flag. Similarly, we had this collision flag in SPI also. Then you have TWI enable pin. As we have some alternate functions on your output pins or port pins, we will have to first enable this TWI on this particular bit such that those alternate functions of working like input output will be disabled, and that pin will be available for TWI interface. Then this is reserved bit, and this is to enable the interrupt, TWI interrupt or I2C interrupt. Next you have status flag. In this status flag, these bits are all only this T7 to 3rd bit is for status register, and this TWS1 and TWSP0 is for prescaler. Just now we have seen in that formula we have 4 power TWPS. TWPS indicates prescalar bits. As you have 2 bits, you can understand you will have 4 combinations 0001 1011. So the prescalar values become 1, 4, 16 and 64.
Okay.
And this particularly is used only for calculating your bit rate. Okay. Now what is this prescalar? Generally what we have prescalar is, in general terms I'll say you, if you are counting 1 to 10, we will be counting it like 1, 2, 3, 4, 5, 6, 10, right?
Yeah.
If you want to count 100, but in terms of 10, I want to count 100, but I don't want to count 1 to 100. I want to count only 1 to 10. So what I'll do, I can say something like 1 to 10 as 1 only, 11 to 20 as 2, 21 to 30 as 3, right? That particular thing you call it as prescalar.
Okay.
Then you have here, you will have one register called TWDR register, where you will receive, or this is a buffer register which will be used for collecting or transmitting or receiving your data.
Okay.
This is address register. Like we have data register, here we have address register also. That is, these are the registers related to I2C in at Mega 16. Okay, so this is the basic or general concept of your I2C also. I hope this is somewhat clear, because generally no one will ask you about registers. Okay, why? Because you have so many registers with so many different microcontrollers that no one will remember registers. Okay, no one will, you cannot remember all the registers, because if you are working with some 10 microcontrollers, you will have 10 sets of registers related to each peripheral. For timers, if you see timers only, in time how many registers are there for 805 in TH0, TL0, which is timer 0. Then we have TMOD register, we have TCON register, right? Then we have one more register, there we are using a PCON, I guess. So 4 registers are related to timer. Like that, 4 different registers are there for different microcontrollers. So you can simply understand the general concept behind these things. You cannot remember registers. To remember or to check out the register, you will have to go with data sheet only. Okay, so we will see more on this later. Why? Because when we are write program for some other controller, or once you become somewhat familiar with other controllers, we will work out with this also. Okay. So today we will end our session with this. If you have any doubts, you ask me.